In this video, we'll talk about the distribution of materials to and from the blood. So, first we'll look at oxygen and carbon dioxide. Now, these, as you know, are gases, and the rate that they leave or enter the blood is strictly based on their concentration gradient and the process of diffusion. This is why capillaries are as small as they can be. Capillaries are the size that allows single blood cells to travel through them. Capillaries have walls that are as thin as can be. These are single cells that comprise the capillary wall, oriented in such a way that they are as flat and skinny as they can possibly be. So a very short distance is necessary for diffusion to be of sufficient rate to be an effective means of moving a material from the blood and to the blood. Water-soluble molecules, ions especially, but small neutral molecules as well, move through spaces in between, these spaces are called pores, in between the cells that comprise the wall. Now there's some complicated structure, extracellular matrix structure there, but the key is that they are pores through which liquid can flow, and that liquid can allow a little bit of diffusion, but a little bit of also bulk flow through these pores so that materials can enter or exit the blood. Now, big things, proteins, for instance, must be moved by transcytosis, endocytosis into the cell, exocytosis from the cell. The fluid through pores into and out of the blood is another case of water potential determining the rate at which water moves. So you'll notice that in this textbook diagram of the process, there are different pressures as you move from the artery or arteriole end of the capillary to the venous end of the capillary. So there's more pressure, bigger arrow, early than late, closer to the artery than closer to the vein. You'll also notice that, although osmotic pressure, I don't know what that means, osmotic potential is the same in each of these locations towards the artery and towards the vein. And as a matter of fact, that factor never changes. That measurable quantity forms a horizontal line on a graph. And so, to show this, I will add this graph to the numbers presented and show you that these are relatively straight line relationships. Here I've graphed your 32 millimeters of mercury blood pressure. Now, this is the difference in pressure, notice, across this membrane. So the interstitial fluid pressure is essentially zero, and so the blood pressure is the difference in pressure across the membrane. So this is a difference. 32 when the blood is entering the vessel, 15 right there when it's exiting the vessel. The osmotic potential doesn't change all the way across. That difference in osmotic potential is what that really is. So there's some osmotic potential out here in the interstitial fluid. There's osmotic potential in the blood. This arrow, this graph line, both represent the difference between those two. And if you think about it, it had better represent a difference because it's somewhere between 32 and 15. 15 and 32, you'll notice, are positive numbers. Osmotic potential can't be negative. This is a positive number because it's the difference between two osmotic potentials. Placing that graph in the context of the whole circulatory system, recognize that the arteries are not allowing transfer of materials. The arterioles are not allowing transfer of materials. It's only in the capillaries that materials enter and exit the bloodstream. And so this is a subset, this pressure part of the curve, of the entire distance from the heart pressure curve. Okay, so I said that this is the difference in blood pressure. It's always a positive number because your blood pressure can't be negative and doesn't quite get to zero in the capillaries. The osmotic potential is really the difference in osmotic potential between inside the fluid and outside the fluid. And you need to remember that it is a force driving fluid back into the blood. Because it's driving fluid back into the blood, it has the opposite effect of pressure. Pressure is pushing fluid out of the blood. Osmotic potential is pulling fluid back into the blood. Therefore, blood has more solute. Blood has a lower osmotic potential than does the interstitial fluid. Now, why this line is horizontal, why this relationship doesn't change throughout the range of distance from the artery, from the vein, of the blood, even though there's materials moving back and forth, why that osmotic potential difference doesn't change is complicated. Don't have to know it for this class. It has something to do with the nature of the proteins that provide the osmoticum, the solute that's in the blood, having a osmotic potential buffering capacity. But suffice it to say that this relationship doesn't change. That is the relationship of osmotic potential in the blood to the osmotic potential in the interstitial fluid. At the point where these two lines cross, you have water potential equilibrium. Remember, there's more pressure in the blood than there is in the interstitial fluid. There's more solute in the in the blood than there is in the interstitial fluid. So this is the balancing. This is the difference in osmotic potential. That's the difference in pressure potential. When those differences are equal, then you have equilibrium. More pressure, lower osmotic potential in the blood. Right? So when those pushing fluid out, pulling fluid in forces are equal, there's no net flow of liquid into or out of the blood. Anywhere before that, the pressure is the stronger influence, and therefore all through this range, throughout this part of the vessel, you have a exit of fluid from the blood. When the osmotic potential is pulling in with an influence that is greater than the influence of the pressure, which is still pushing out, but not as hard as the pulling in influence of the osmotic potential, you have entry of fluid back into the capillary. This is necessary, otherwise your blood volume would be reduced in the capillaries more significantly than it is. Now, I have to admit, this system isn't perfect. There is a little bit of fluid loss typically. That's one of the functions of your lymph system. Your lymph system gathers up some of the extra fluid that's deposited. But by and large, you want to balance fluid loss, fluid return, so that the blood volume stays the same. This helps with distribution of goodies and removal of waste from the interstitial fluid that is bathing the tissues that this circulatory system component is servicing. So, what kinds of questions might you be asked on this relationship of osmotic potential and pressure potential, I often give you the range of pressures in a vessel as it moves from the arterial end to the venous end. Right? So this would be in perhaps kilopascals or megapascals, maybe millimeters of mercury. If I were to tell you that fluid begins to enter the blood at 10 micrometers from the arterial end, what do you do with that information? Okay, so if at 10 micrometers from the end, I have fluid beginning to exit, that means before that, fluid was exiting. So it's beginning to enter here. That means that before that, the osmotic potential was a weaker influence. After that, the osmotic potential is a stronger influence. We know then that it is at 0.07 in this graph, units of pressure, that equilibrium is reached. We know that equilibrium is reached only when the osmotic potential and the pressure potential are equal. So we know that in this case, where this was the information given, you've got a pressure and an osmotic potential defined. Another example of variables I could give you. I could tell you the osmotic potential of the blood. And so let's say the osmotic potential of the blood was, I don't know, minus 0.1 units. Minus osmotic potential of the blood. And I can tell you that the osmotic potential of the interstitial fluid was, let's say, minus, it has to be, you'll notice, a greater number than that of the blood. The interstitial fluid of the blood is always going to have a lower osmotic potential than that of the interstitial fluid, so that limits the choices I have. But let's say it's minus 0.02. What does that tell me? Well, it's your job to remember that the difference in osmotic potential that we graph to get a positive number here so that we can compare it to the pressure potential, that difference is going to be minus 0.02, the osmotic potential of the interstitial fluid, minus 0.1. So what is that? Well, minus 0.02 minus 0.1 is 0.08. Okay, and if that's true, then that's the difference in osmotic potential in the blood and the interstitial fluid, and I can graph there. And I can see that, I don't know, somewhere along that basis, so somewhere in between 8 and 9 micrometers is where the blood stops exiting, the fluid stops exiting the blood and begins to enter the blood. I could have given you the difference in osmotic potential and one of these two values, and you could have used algebra to get the other. Again, I could give you the distance from the blood. I can give you the pressure at which that happens and an existing line without giving you the pressure line. There's not that many variables I can change, but I can change any of them and expect you to be able to understand this graph rather than memorize it and solve questions accordingly. Now in the homework, I think I remember that the liver had a malfunction and added solute to the blood. Now if I add solute to the blood, does the difference between these numbers become reduced? In which case that line would go like that, lower. Or does it become increased? In which case the difference would be higher. So if you add solute to the blood, does that make it more negative or less negative? That's what you need to think about to solve that homework.